In our continued discussion about optics, we're going to move on to Module 11. Module 10 dealt with reflection of light, and now we're going to discuss refraction of light. So what is refraction? Refraction is a phenomenon, in a nutshell, where light bends due to its encountering other media. The classic example that's often discussed or pointed out when dealing with refraction is the illusion that you see when you have a straw in a glass of water and it appears as though the straw is disconnected, because effectively what's happening is that the speed of light in the medium of the water is much slower than that of the air. So when we talk about the speed of light, we often just act like it's one speed, c. c, which is equal to 3 times 10 to the 8 meters per second, is the speed of light in a vacuum. Anytime light has to go through some other medium, such as air or water or glass, then the speed of light, for example in air, is going to be less than this c. Now it turns out that the speed of light in air is actually approximately equal to c, but the speed of light in, say, water is a good bit slower than c. And so whatever medium your light is going through, what we generally talk about is what is its index of refraction. Sometimes we talk about the velocity, but a lot of times when we're dealing with optics, we talk about its index of refraction. The index of refraction is indicated by the letter N, and the letter N for the index of refraction is going to be equal to the velocity, the speed of light, I read the wrong thing, the speed of light here divided by the velocity of light in that medium. So speed of light c being the velocity of light in a vacuum divided by the velocity of light in whatever medium you're talking about. So there will be different indices of refraction, different n values for different substances. So you can imagine then, well, what kind of number is this going to be? If I was actually in a vacuum, then I would have c divided by c, and that would just give me the number 1. Anytime I am in something other than a vacuum, then this denominator, this velocity, is going to be smaller than the numerator, because nothing can exceed c. You're always going to be somewhat slower than c. And so this number, with the denominator being smaller than the numerator, will be greater than 1. So in general, this number has to be larger than or equal to 1. And the only time it's going to be equal to 1 is if the light is traveling through a vacuum. Notice that there are no units here. That makes sense because we're dividing a velocity by a velocity, so meters per second divides by meters per second, and we have a unitless quantity. Okay, so I want to quantify this phenomenon of refraction further and introduce a law that governs how much bending of light occurs. We had the law of reflection to help us describe how the bouncing of light off of something takes place, and that was a pretty simple relationship where the incident light just equaled the reflected light. For refraction, it's a little bit more complicated. We have to consider what substance we're dealing with and what its index of refraction is. And then the relationship that applies here, Snell's law, or the law of refraction, tells us that the index of refraction times the sine of this angle theta 1 will equal the index of refraction times the sine of this angle theta 2. These angles are measured with respect to the normal of the interface between one substance and the other substance. So I draw a perpendicular line to this interface, and then I measure the angles with respect to that perpendicular line. If you think about what actually is happening with the index of refraction, you can get a sense of whether this should bend towards that normal line or away from that normal line. If you are moving from a substance in which the speed of light has to slow down a lot to a substance where the speed of light can take place a little faster, then what's going to happen to your indices of refraction on the left side versus the right side of the equation? Well, I'm going to have a larger index of refraction here for N1 than what I have for N2, which means that theta 2 has to be larger than theta 1. That is to say, if I'm going from a slower substance to a faster substance, the refraction will be away from this normal. This theta will grow larger. Now, if I simply reverse the directionality on this cartoon here, let's just imagine I'm going to go the other direction here. And I'm going to go from the fast substance to the slow substance. Now I've got a smaller index of refraction to a larger index of refraction. And so this angle theta 1, well, the refracted angle, we'll just say, has to become smaller than the incident angle. And so when you're going from a faster substance to a slower substance, for example, from air into water, like we had with the straw in the cup, then the refraction will bend towards the normal. I really encourage you to click on this link here that you see. I don't really want to take the time to play the whole video for you within my own video, but it's highly entertaining and it gives you some good analogies to think about as to why this sort of bending will occur when these rays of light go from one substance to another substance. Okay. So I think this will also be, before I get to the example, I also wanted to show you some examples of different indices of refraction. So these are different N values, and you can find tables like these online and in your textbook. But as you can see, because the speed of light is very close to what it would be in a vacuum whenever light travels through air, then the index of refraction is very, very close to 1 for air. But other substances have indices of refraction that are noticeably different from 1. Notice, like we said before, that n is always going to be greater than or equal to 1, so all of these are greater than 1. And so you can see that when you're going through water, you've got a higher index of refraction, glass even higher, diamond even higher, and so on. So let's do an example where we utilize the law of refraction and we try to learn something about an unknown substance that light travels through. So you're given here an incident angle and a refracted angle. And the assumption that we're making is that the light ray coming in is coming in from air and going into some unknown liquid. So we can draw a picture of this. This can be my interface between the air and the unknown liquid. And then I'm going to draw a perpendicular or normal line with respect to that interface. Okay, and then I'm going to draw some light ray coming in at an angle of about 30 degrees with respect to that normal. And then as it's refracted, it looks like it's bending towards the normal because the refracted angle is only 22 degrees. So already we can deduce that I must be going from something that is faster moving, that light can move faster into something that light can move slower in. But that makes sense because we're going from air to start with, and it's got an index of refraction very close to 1. It's very much the same as traveling through a vacuum, and so just about any substance here is going to slow the light down. And now we need to dig a little deeper to try to learn what that substance might be. Okay, so let's take the equation for Snell's law, N1 times sine theta 1 equals N2 sine theta 2. And let's look at what it's asking us. It's asking us how fast the light will be traveling through this unknown substance. Well, these are the indices of refraction, but we can make a simple substitution in here that will express this second index of refraction in terms of the speed with which the light is traveling through that substance. So we can replace N2 with C times V2. C over V2, sorry. I wrote it right, said it wrong. Okay, and so with N1 being air, we can make this a little bit simpler and just take N1 to be equal to 1. Okay, and then we can simply solve for the velocity V2 that we're looking for. So C times sine of theta 2 divided by sine of theta 1 will equal my V2. So if I plug in the numbers here, C times sine of 22 degrees divided by sine of 30 degrees, what I should find when I plug that into the calculator is approximately 2.25 times 10 to the 8 meters per second. Okay, so that answers the first part of the question of how fast the light is traveling through the substance. And so now I want to try to figure out what the substance, for the second part, what the substance could be. So now I'm going to go back to the index of refraction, N2, and I'm going to remind myself that this is C divided by V2. And so if I plug in 3 times 10 to the 8 divided by 2.25 times 10 to the 8, what I should find is that the index of refraction for this unknown substance is equal to 1.33 approximately. So referring back to my chart here, that appears to correspond with water. Okay, so, oops, I keep skipping ahead a bit. So that's an example of how you might use Snell's law in practice, and what you might be able to deduce from it, such as the speed with which the light travels through the substance, or its index of refraction. Other times you might be solving for the refracted angle, and so on. All right, but you might wonder, well, how extreme could refraction actually be? Does this bending of light actually, how much can I make it bend? And it's a good question. If you're dealing with some sort of interface at a fairly large angle, then the refracted angle can be even greater if you're going from, say, a slow substance such as water into air. And as I change that incident angle to make this refracted angle larger and larger, I can reach a point where it is so refracted that it's just skimming the surface here. It's essentially perpendicular to this normal line, which is to say that it's really not being transmitted at all into the air. Beyond that, if I increase this incident angle even further, then I've made the refracted angle, as demanded by the law of refraction, so large that what happens is that it's even greater than perpendicular. This becomes an obtuse angle, and the light is effectively reflected back into the original substance, so that it can't be transmitted at all. It's refracted so much that it's reflected. All right, so for different substances, different transitions, say from water to air or from glass to air, this critical angle here, where it's not transmitted at all, it's just skimming the surface, it's perpendicular to the normal, will be slightly different. It will be dependent upon what these indices of refraction are with respect to one another. So we can derive a relationship that will tell us what this critical angle is, beyond which I will always have what we would call total internal reflection, or refracted so much that it's reflected. The derivation basically just starts with the law of refraction, Snell's law, and plugs in this value 90 degrees, right? This is our critical angle here, on the right-hand side of the equation. Now, we know that the sine of 90 degrees is simply 1, right? So this simplifies. And if I solve for the critical angle, then this tells me that the critical angle is always going to be equal to the inverse sine of N2 over N1. Okay, now this is only going to happen in a situation where N1 is less than N2. Otherwise, this equation does not make any sense. And if you think about what's happening in terms of the light being refracted either towards or away from the normal, that also makes sense, because I need for this angle to be larger than the incident angle, or otherwise I will hit 90 degrees here before I hit it here. Okay, but so long as I'm going from some place where the speed of light had to really slow down to some place where it can go a little faster, I can achieve this total internal reflection. Okay, and so let's do an example where we find out what the critical angle is for a specific substance. So let's imagine that we have a diamond surrounded by water. So we have a diamond immersed in water. And we want to know then what the critical angle is for this situation. Okay, so we're going to take the equation that we just derived on the previous page, that the critical angle is going to be the inverse sine of N2 over N1. And we're going to plug in the values that we see here on the chart for the two substances involved, which are water and diamond. Okay, so the N2 is going to be the water and the N1 is going to be the diamond, right? Because I need for N1 to be, I need for this condition that we're seeing here to hold. Okay, so we need that ratio. Sorry, this is disappearing on me. Okay, so if I plug in the values here, then what I find is that the critical angle in this case is 33-ish degrees. Okay, the second half of the question I'm going to have you do as an exercise. What if instead we surround the diamond by air instead? You can see that that's really only going to change one value here in this equation, and you can see how those angles compare. Okay, so one thing that we've ignored, or I guess oversimplified in this discussion so far, and really the last thing that I want to discuss in this lecture, is the fact that refraction actually depends upon the frequency of the light. So we haven't really considered what color of light is going through my medium, but refraction actually bends the light in a frequency-dependent way. And so if you've ever seen the schematics of white light coming into a prism and breaking it up into its constituent colors of the rainbow, the reason that that occurs is because the blue light is going to be refracted to a greater extent than the red light, and all the colors in between are somewhere in between those two extremes, and so it causes, when it emerges from the prism, to emerge in different places due to the more or less extreme refraction. We're not going to quantify this, but I just want to give you a qualitative description so that you understand conceptually what's happening. And so we're familiar with this phenomenon as it applies to seeing rainbows in everyday life. Rainbows are happening by a combination of refraction, total internal reflection, and then this frequency dependence that we call dispersion. Okay, so what happens is that the incoming light from the sun hits so many different water droplets in the air, and when it enters the water droplet, it is refracted in a frequency dependent way, and then there's total internal reflection that occurs within the droplet, and then when it emerges again, it's refracted again in another frequency dependent way, so that when the light reaches your eyeballs, what you see is the red on top. And then, you probably know your colors of the rainbow, the Roy G. Biv. So then the orange is somewhere over here, and then the green below it, and the blue below that, and then violet, and so on. Okay, more if you click on the link, and we will also talk more about refraction in the next lecture. Thanks for listening.